Okay, so this is a video on density curves, normal curves, and standard normal curves and how they all relate to each other. I have a student right now that's taking a statistics test, and I thought I'd make this video to not only help him, but to help other people struggling with this. So, what is a density curve? Well, a density curve is a curve, obviously, and it's got two main properties, as you'll see there in blue. The two main properties of density curves are that the curve lies entirely on or above the x-axis, and the second property is the area under the curve is 1. So, taking you right into normal curves. Normal distributions are represented graphically by normal curves, and they look like the curve I drew below, which is my best attempt at a normal curve. Now, before we start to talk about normal curves, let's talk about normal distributions. Normal distributions are distributions that are very common in statistics. They're very frequently seen, and we can say some things about these distributions. The curve looks like that bell curve right there, and right here at the vertex of the curve, so if these are your values, this is the mean. So this is the mean right here. And then where it starts to dip a little bit, and this is not the best drawn normal curve in the entire world, but this is like one standard deviation out. So it's like the mean minus a standard deviation, and this is a mean plus a standard deviation. And then you can continue on, and then this is a mean plus 2 standard deviations, and this is a mean plus 3 standard deviations. And I'll get to why this is important in a second. So here's a mean minus 2 standard deviations, or 2 standard deviations below the mean. And here is a mean minus 3 standard deviations, so that would be 3 standard deviations below the mean. So that's generally what a normal curve looks like. And we're going to move on to talk a little bit more about a property of a normal curve that's very important to know. So here's another normal curve. It's not quite drawn as good as my first normal curve, but it's the best I could do. So right here, as I said, is the mean. And I'm kind of just going to do this again. This is the mean. And then this is one standard deviation above the mean, so it'd be the mean plus a standard deviation. And then this right about here is, and we can continue going, 2 standard deviations below the mean, 3 standard deviations below the mean, and here we just need to fill in the rest of it. So this would be 2 standard deviations above the mean and 3 standard deviations above the mean. Okay, so now that we got that, I can start to tell you about this rule, the 68, 95, 99.7 rule for normal distributions. Okay, so the first rule in this set of rules is 68% of data falls within 1 standard deviation above and below the mean. So here is 1 standard deviation above and below, and we know that 68% of the data falls in there. One thing I didn't say about normal distributions are that they are symmetric. Normal distributions are symmetric. They're symmetric and they're bell-shaped. So from here to here, since they're symmetric, 34% of the data falls from here to the middle point. And then 34% falls from here to here. Okay, second part of the rule. I'll do pink now. 95% of the data falls within, and that should be a within up top there, within 2 standard deviations above and below the mean. And so above and below the mean. And we know that 95% of the data falls in there. So you can say that, of course, you could say that 47.5, which is half of 95, falls there, and then half of it falls in there. Okay, because it's symmetric, remember, it's symmetric. Okay, so the last bit is that 99.7% of the data falls within 3 standard deviations above and below the mean. And so here's 3 standard deviations, and we know that 99.7% of the data falls within this green range. So 99.7% of the data falls in that range. So what falls outside here? What falls outside here? What percent of the data falls outside here? Well, we know that if 99.7% of the data falls within those, then that's 0.3% left outside 3 standard deviations above and below the mean. And so you'd have about 0.15% over here, and you'd also have 0.15% over here because, again, normal curves are symmetric. That's one of the things you can assume when you're told you have a normal distribution. You can assume you have a curve that looks like this. You can assume it's symmetric. You can assume it's bell-shaped. And you can assume this 68, 95, 99.7 rule for normal distributions. Okay? All right, moving on to standard normal curves. So we had density curves. We hit that. We said density curves were curves that lie entirely on or above the x-axis and have an area under the curve equal to 1. And we said, okay, these normal curves are density curves, so they assume these 2 properties, as well as a bell shape, symmetric, and the 68, 95, 99.7 rule. And now we're going to look at standard normal curves. So a standard normal curve is a normal curve. Now, it's standard because what we do is we standardize a variable. And I'm going to discuss some of this now. So if some statistic has a normal distribution, then we may standardize that data. And this is the way we do it. We do it as this new standardized variable, z, is equal to whatever the variable was minus whatever the mean was over whatever the standard deviation was. Okay. So let's talk about this for a second. And I'm going to do it with an example. So before I start the example, I should say that SAT math scores are scored on a scale from 0 to 800. So that is something you should know while looking at this problem. The problem says if SAT math scores take on a normal distribution, so once you see that it takes on a normal distribution, you can assume the normal distribution, you can assume that 68, 95, 99.7 rule, you can assume symmetric property, and you can assume the bell-shaped curve. And its mean is mu equals 520. That's mu is the Greek letter for mean in statistics, and a standard deviation of sigma equals 50. What percent of SAT math scores fall? And I broke these up into colors because the red ones we can use the 68, 95, 99.7 rule on, and the blue ones we're necessarily going to have to use this idea right up here. So I want to know what percent of SAT math scores fall between 0 and 520. Well, if we take a look at our, let's look at our normal curve, and hopefully I can draw it good. It's probably the best one I drew. So again, this is the mean, and the mean is 520. And basically the first question is asking me what percent of the data falls from 0 to 520. So if 0 is somewhere out here, right? And it's all this stuff right here. So what is that? Well, it's half the area under the curve, and since we know that standard normal or normal curves are symmetric, we can say 50% of the data falls between 0 and 520. Okay? Now, I'm just going to erase that shading I did. And, oh, a little bit too much. And so we can say 50% falls between 0 and 520. Okay, now let's add some standard deviation. So what's the standard deviation? 50, right? So what would be one standard deviation below the mean? It would be mu minus 50, right? So that would be, it would be 470. And then another standard deviation below the mean would be 420. And then another one would be, 370, right? And then 0 is way out here. 0 is way out here. Not many people get 0. So one standard deviation above the mean would be the mean, which is 520, plus the standard deviation, which is 50, so it'd be 570. And then another standard deviation above the mean would be 620. And then another standard deviation above the mean would be 670. And very few people get above 670 in America. So, we want to know the percentage of data that falls between 420 and 620. Well, isn't that just 2 standard deviations above and below the mean? So we know by our 68, 95, 99.7 rule that that would be 95% of the data, right? Because we said back here that 95% of the data falls between 2 standard deviations above and below the mean. Okay, so last one that we can use the 68, 95, 99.7 rule for is part 3, and it says how much of the data falls between 570 and 800. So 570 is right here, and we want to know what is the area of that shaded region. Okay, we know the area under the whole curve is 1, so what's the area of that shaded region? Well, what are some things that we do know? We know that from the beginning of the curve to here, the 50% point is going to be 0.5 or 50%, right? And then we also know that this bit between the mean and 1 standard deviation above the mean, what did we say back here? We said that was 34, right? So we know that this is 0.34. And so remember, the area under the whole curve is 1. So if we just subtract 0.5 and 0.34 from 1, we get what we want, which is this bit right here. We want this bit. And so 0.5 minus 0.34 is 0.84. And so 1 minus 0.84 is 0.16. So that's what this is, 0.16 or 16%. Okay? So now that we're on to these 2 questions, I'm going to review this concept of standardizing data now. So again, if you're told that a statistic has a normal distribution, that the distribution for the statistic is normal, then you may standardize the data, and basically you can take some piece of data, x, and give it a new value, z, corresponding to this formula, z equals x minus mu over sigma. So the statistic minus the mean over the standard deviation. So I'm going to go to the next page, and I'm going to draw a normal curve, and I'm going to kind of rewrite the important parts of the problem. So I'm going to write that, and I'm going to write that, and I'm going to write these things right here. So here we go. And we said that mu was 520. We said that sigma, the standard deviation, was 50. We said that we want to find, what do we want to find? Between 0 and 500. And what else do we want to find? 400 to 650. And we want to find percentage of data between those intervals. Now, since we're looking at the percentage of data that falls between those intervals, and all the data that we take is in this distribution, then we can say that the probability of a score being between 0 and 500 and the probability of a score being between 400 and 650, which is written like this, so the probability that x is between 0 and 500 and the probability that x is between 400 and 650. That's exactly the same question that we're asking here. So that's exactly the same question that we're asking. It's just a different way to word it. So it's like, what's the probability somebody scores between 0 and 500? What's the probability that somebody scores between 400 and 650? That's the same question as find the percentage of data between those two numbers. Okay, so let me just draw a normal curve and let me explain to you why we have to use standardizing of a variable here. So okay, so again, this is the mean, and the mean was equal to 520, and then one standard deviation. This is probably the worst normal curve I drew. One standard deviation above the mean is 570, and another standard deviation above the mean would be 620, and another standard deviation above the mean would be 670. We said that before. And again, it's 470, and then 420, and then 370. Okay. Well, why do we have to standardize the data? Because unlike these guys, we don't have those values on our curve yet. They're not one standard deviation or two standard deviations or three standard deviations above the mean, but they're other things. So, okay, so let's look at number 4. For that problem, I'm going to use pink. We want from 0, which is all the way down here, 0 is all the way down there, to 500. Okay, so let's say 500 is, maybe it's like right about here. It's 500, right? And we know that the area under the curve is equal to the percentage of data that falls in that region. So we want this area under the curve. Okay, well, how the heck would we get it? We have to use this idea of standardizing variables. Okay? So this right here, the probability that x lies between 0 and 500, really, since 0 is the lowest score, you can say that's the same as the probability of x being less than or equal to 500. Now, what I'm going to do is standardize this variable right here, x equals 500. So we have x equals 500, right? And I'm going to standardize it. I'm going to call it z1. So z1 is going to be, this is x1. Let's call this x1. z1 is x1 minus mu, so minus 520. I'll just put mu over the standard deviation. So given what we know, it's 500 minus 520 over 50. So that's going to be negative 20 over 50. And that's going to be negative 40 over 100. Same thing. So it's going to be negative 0.4. So Z1 is negative 0.4. And essentially, what I'm going to do here is say, okay, the probability that x is less than 500 is the same as the probability that z is less than or equal to negative 0.4. Okay, so what does that mean? Well, if this is a standard normal curve, and I'm going to draw another standard normal curve here. This right here is a normal curve, and then we standardize it. You know what? I'm going to do this on the next page. So we standardize it like this. So here is a standard normal curve, and it's just a normal curve. That's bad. That looks better. Okay, it's a normal curve, and right here where the mean is, this is always z equals 0. Right here is one standard deviation above, and that's going to be 1. And this right here is going to be 2, and that's going to be 2 standard deviations above. The mean, obviously. And this is 3 standard deviations above. Now over here, we're going to have negative 1, we're going to have negative 2, and we're going to have negative 3 for 3 standard devs below, 2 standard devs below, and 1 standard dev below. And that's how the standard normal curve is set up. So basically, again, what percentage of the data lies in here? 68%, because it's a normal curve, right? It's 1 standard deviation above and below. But basically, we standardize it into this variable z, which is easier for us to work with. And they all standard normal curves have tables that you can look up, and here is one right here. So look at, like, basically what I want to show you here is that this curve and this z right here, this is the area to the left of the curve, and that's what all these guys are. They're the areas to the left of the curve. So you'll notice if, like, you know, we pick z equals 3.05, so that would be that row and this column, and you just find it and it'd be right there. We see that the area under the curve is for z equals 0.9989, so 99.89% of data lies to the left of z equals 3. So that's basically what a z table is. It helps you find for a particular z value. So for instance, like negative 1.55. Let's look up the area under the curve. So let's say this is negative 1.55. What area is here to the left? Well, I'd go down to negative 1.5. It's right here. And then I'd go to 0.05, and I'd just look there, and I'd say, okay, it's right here. So that would be the area under the curve there is 0.0606, or 6.06% of data lies to the left there. And it's always to the left. It's always to the left. When you're reading these tables, it's always to the left. Okay. So there you go. That's what it is. Now, back to our problem. We standardized this 500, and we said that the percentage of the data that lies between 0 and 500 is the same as the probability that the piece of data or the score is between 0 and 500. And we said, okay, since 0 is the lowest, basically it's the same thing as saying the probability that the data is less than a score of 500. And then we standardized the data, and we said, okay, 500 is the same as this z right here. Probably won't put that. It's the same as negative 0.4. So basically, the probability that z is less than negative 0.4, we would go to our chart, and we would find 0.4. Where is it? 0.4 looks to be right around here. It looks to be, let's say it's right here. This is the closest thing we can get to it. Now, what is that? Now, that's down here. Oh, my bad. I'm actually doing the wrong thing. I'm sorry, you need to find negative 0.4 on z. So this is the z's right here. In the middle is the area under the curve. We're looking for the area under the curve. So we're looking for z equals negative 0.4. So again, we go down this column because this is the negative column. And we find it right here, right? And what column is it? Well, this is the row, negative 0.4, and this is the column, 0.00, right? Because that's what we want. We over here, so 0.3446. And that is, so what percentage of the data? So 34.46 lie between 0 and 500. Okay, so now we're going to do the same thing for this next problem. So again, the 400 and 650. I'm sorry if I said one of the numbers wrong. It's 400 and 650. So let's just plot them on the curve here. So 400, and we want to find the percentage of data that lies between these guys. Normal curve in that chart we have. So we want to find the area under the curve that I scribbled in red, right? And first we need to standardize these two guys. So I'm going to call this x2, and I'm going to call this x3, and I'm going to say z2 is equal to x2 minus mu over sigma. And so that's going to be 400 minus 520 over sigma, which is 50, right? And so that's going to be negative 120 over 50. And that's the same as negative 240 over 100, and that's the same as negative 2.4. So z2 is negative 2.4, and what's z3? z3 is going to be x3 minus mu over sigma, and that's going to be 650 minus 520 over 50, and 650 minus 520 is 130 over 50. And that's the same as 260 over 100. And so Z3 is going to be 2.6. Okay? So 4, and I should write that bigger. Oh, computer freezing a bit. Computer is freezing a bit. Oh, my computer is freezing. This is not good. We're good. And 2.6. Okay, let's go to our other page. So, okay, so this is equal to, and this is the difficult part, so try to bear with me. This is the same as this area from here all the way to the end, the leftmost you can go, all the way to here. So that's the probability that z is less than or equal to 2.6, because remember, we're always trying to deal with to the left of things, to the left of 2.6. Okay, it's that minus, so what is that? I should draw that in. That's all this. I don't want to use that color. That's all this right here. Right? That's all this right here. Minus this bit right here. And then you'll have everything, at that point, you'll have everything from here to here, right? So we subtract what's in the green minus the probability z is less than negative 2.4, and you have your answer. So what's the probability z is less than or equal to 2.6? So we go to our chart, and we say, okay, where's z equals negative 2.6? Or negative 2.4. Is it negative 2.4 or negative 2.6? Sorry, it's not negative at all. It's 2.6. So we go over here to 2.6, and we're in this column, and it's 0.9953. So we go back over here, and we say this, we go to negative 2.4, which is right here, and we use this column, and it's 0.0082. And so that would be 0.0082, and your final answer then would be what? It would be 95 minus 8 would be 87. Yeah, I think that's it. Yep. It'd be 0.9871. So 98.71% of scores are between, what did we say? We said 400 and 650. And remember, the way I did that was the following. I said, okay, I wanted to find this, right? Okay, well that's there and that's there. They're not 1, 2, 3 standard deviations above and below, so we can't use the 68, 95, 99.7 rule, so I have to standardize the data. So here I am, I said this right here is the same as this right here because I standardized the data right here, and I got that 400 was the same as negative 2.4, and I got that 650 was the same as 2.6 if we're talking about z's. And so then I said, okay, this statement right here is equivalent to this statement right here. And then I moved over here and I plotted those two z's on our z standard normal curve. And I wanted the area between those two guys. And I said that's equal to the area to the left of this 2.6 minus what's to the left of this 2.4. That left us with the area in the middle that we wanted. The area in the middle that we wanted. So I said, okay, the area to the left of 2.6, I looked on my chart and I found it was this, and then I wanted the area to the left of negative 2.4 to subtract from it, and I found that it was this. I did the subtraction and I got my answer. So again, we went over density curves. They're curves that lie above or on the x-axis. The area under the curve is 1. A normal curve is a density curve. It's a special type of density curve that's symmetric. It's bell-shaped. It's got the 68, 95, 99.7 rule that states 68% of the data lies between 1 and standard deviation above and below the mean. 95% of the data lies between 2 standard deviations above and below the mean, and 99.7% of the data lies between 3 standard deviations of the mean. Sometimes when you're dealing with normal distributions, it's very helpful to standardize the data, so you can use this standard z-curve, and you standardize the data by taking the piece of data, subtracting it from the mean, and dividing it by the standard deviation. That gives you a thing we call a z-score. Then you're able to use a table like this to help you find the area under the curve. I hope this was extremely helpful, and if you need any help for mathematics, I would encourage you to visit onlinemathacademy.com. I got a lesson right now, so I gotta go. Talk to you later.